sampling integration method, a crazy new algorithm, which answers the question if the masters in the 16th, 17th century had programmable calculators or computers, they would come out with an algorithm like that. But it had a little bit extra computation to it, so I'm sure they shied away. The genesis and history of this algorithm in the 1980s, I used to travel a lot and write HP41C programs after hours that I would send to Corvallis. And I wrote a program about this method. And I figured, well, I can do numerical integration if the numbers are, the values of x are not equidistant. And I sent it there, they accepted it, and I forgot all about it. And recently I found it on the HP Museum DVD. And I thought like, hey, this is cool. Somebody, you know, that was part of maybe about 6 programs somebody salvaged. So I read it again and go, you know, let me dig in the method again. So I had a renewed interest in it, and I expanded on it. One of the things about integration methods is that the ability to divide the integral into subintegrals, which means you can use a method on, say, if you can use any method on the subintervals and just repeat the same. You don't have to apply the method on the entire subintegral. This way you can increase accuracy. So you calculate the integrals on the subranges and then add them up, and you get the big integral you want. Most common algorithms sample the integrals at regular x values. This includes the Simpson's 2 rules, excuse me, and other Newton code methods, open and close. Another class of algorithms is the Gaussian quadrature, and they sample the integrals at special values that happen to be the roots of special polynomials like the Legendre, Laguerre, Hermite, and Chebyshev. And they actually yield very good values. The new variable sampling integration method, I'm calling it VSI for short, samples the integral range at non-equidistant. There's no rule. It's kind of free form, you know. I'm going to explain the method briefly in visual form first before I get into more details. This is a depiction of, say, y equals 1 over x, and I have the function in red, and then the intervals that make up the integration range. Notice that when the absolute slope is high, as in that is when the function is changing rapidly, my intervals are narrow because I want to keep track where the function is. On the other hand, when the function slope is low, I don't have to sample it as densely because there's not a whole lot happening. I can sample at wider intervals. Yes.
It shouldn't be the slope. It should be the change of the slope that's important. The more it's changing, the more you want to sample, I think.
No, I do the slope anyway.
Okay.
Here's an example. For example, that I start by calculating the area under the first subrange. Here, I take 2 intervals. The number of intervals I take equals to the power of the interpolating polynomial, or the polynomial I'm going to use to curve it. So here I have 2 intervals, meaning I'm using a quadratic polynomial. I have points x1 at x1, x2, and x3. So I calculate the coefficients of the quadratic polynomial that passes through these points. Once I have those coefficients, then I do analytical integration, and I get the area for the yellow, the area under the curve shown by the yellow color. Then I move on to the next subrange. Now here the green is what I've done so far. The yellow area is the subrange that I'm focusing on right now. Again, now notice x3 was the last point in the first subrange, becomes the new point, the first point in the new subrange, and I add 2 more points to it. And again, I calculate the coefficients of the quadratic polynomial that passes through these 3 points, do an analytical integration to obtain the area in yellow. And I repeat that on and on until I get the whole curve. Now, that's the easy part. The tricky part is, how do I get the values at x values? And that's, I have a lot of options. When we're doing the integration method, of course, we have a range to integrate. Now we select manually or calculate an array or a sequence of x which we need, which does not need to be of equidistant. And then, as I explained visually, we fit a series of quadratic or even polynomial for increased accuracy for each 3 or 4 points on the integrated function. Now, these interpolating polynomials, the one I'm fitting at every 3 or 4 points, where do I get them? I can use Lagrangian polynomials. I can use Newton divided difference polynomials. I can even use Vandermonde polynomials. I can even do curve fitting and get the polynomial. It would be a perfect curve fit. That's a little bit expensive on the calculation side. All these are a little bit more expensive computationally compared to traditional methods. But in the conference the documentation, I'm focusing on the first two. Now, normally, the Lagrangian polynomial and the Newton divided difference are used for interpolation. And what we do, we implicitly calculate the coefficients of the polynomial, but we don't see them because we move on to calculate the interpolated value. What I'm doing, the technique here, is I'm stopping halfway and say, I want the coefficient of the polynomials, thank you very much, and I stop. Then I can go and use it in my integration process. And here, of course, we have the two forms. The quadratic polynomial for each subrange is in that form, or the cubic polynomial is in that. Once I obtain these coefficients, I can do just an analytical integration. I don't have to worry about the original function. And so, as I showed you in the graphs, I calculate and sum up the areas of the smaller areas. That's an advantage of the numerical integration. And so I have a series of polynomials, each for a certain subrange, and then I add all the subranges, and I get the area that I want. Going back now, focusing on x. Now, you can select the array of x manually. That's how I started. When I started this algorithm, I would just eyeball it and select it. And that works fine if you have relatively small values, like 20 values. You can eyeball it. And what you do is you increase the density of the sampling density when the function is changing a lot, and relax it when the function is coasting along. Of course, that can get a little bit more difficult for a function that's fluctuating. And so automation becomes a little bit more practical. So we can calculate an array of x ahead of time when we accommodate that, when we can accommodate the size of the array. And that works fine with like Excel, MATLAB, the 39G2. But the old vintage machine, that can be a problem. So an alternative to that is we can calculate a dynamic sequence of x values in sets of 3s and 4s. So instead of accumulating them in an array, we can just calculate them as we need them. And that saves us tremendously on memory. For example, in the case of the 34S, I couldn't use the array. I contacted the software authors, and I said, I have this problem, and they said, no, you cannot go beyond so-and-so memory size. And I said, okay. And that's when I said, I need to switch to figure out a sequence of x. And that turned out to pay well, a good payoff on saving memory. So the way I start, if I want to automate calculating x, is I scan the integral range at intervals, it doesn't have to be really close, and I look for the minimum and maximum absolute slope values. Once I'm done, I simply calculate the average slope value, just take the average of the other two. So I have 3 slope values. Then I assign increments for x to be associated with the minimum, average, and maximum absolute slope values. So now I have 3 points, and I calculate the coefficients for a quadratic polynomial that correlates the 3 absolute slope values and the 3 increments, x increments that I've assigned. And I obtain a polynomial h of s. S is the absolute slope value, and h is the increment. And I'm going to use that throughout the integration. That will be my guide to tell me how fast or how slow should I proceed from one point to another. And I start the integration at the low integral limit, x equals a, the lower bound. There I calculate the absolute slope, s, at that value. And with s, I go back to that polynomial, I calculate the increment, h of s. And so I'm ready now to take my first step. I increment, I add x to h of s, I get the new value of x. And I start repeating the calculation. I calculate the new slope, absolute slope value for the new x. And I calculate the increment based on that, and I repeat that process until, and most likely, I will step beyond the upper integration limit. When I do that, I take the upper integration limit as the last value of x, because otherwise I'll be introducing errors. I shouldn't do that. In the case of you using an array, make sure that the number of elements match the sequence of the 2n plus 1 or 3n plus 1 if you're using quadratic or cubic polynomials. That's how many you need. So now, normally, when you're calculating the array, if you're lucky, if the pattern, if the number of x's fits that pattern. If not, you have to insert 1 or 2 points in the last subinterval. And that's not a problem because our basic rule is x don't have to be equidistant, so there's no violation of rule. In the case of the sequence, generating a sequence of x, we have to monitor if we have arrived at the end. And in the last sort of subinterval, we may again need to insert 1 or 2 points in the sets of 3 or 4 points that we're having. And we adjust that to accommodate the integration limit. Here's a first example. We're integrating 1 over x, which is the natural log of x. I'm using output from MATLAB because it's very convenient for this talk. And each output has 2 tables. The first table, we have a column showing the range of integration. VSI means the result returned by the variable sampling integration method. And third column is the value returned by Simpson's integration method. And the last column is the exact value of the integral. Second table is, again, the same range, showing the error in VSI compared to the error in Simpson's rule, and then the number of iterations. What's that? That's the number of sub-ranges that I use to calculate the variable sampling integration method. Once I obtain that number, when I'm done, I turn around and use it with Simpson. Why? So I can compare the 2 methods on an equal footing. Otherwise, it would be an unfair comparison. In this case, I'm integrating 1 over x using the quadratic interpolation. And as you can see, I'm underlying where VSI does better. In the second and third range, VSI does better than Simpson. When I move from quadratic to cubic using the same ranges, I forgot to mention, I'm going from 1 to 2, 1 to 10, 1 to 100. So the first range, I'm in the same magnitude. The second range, I jump 1 magnitude, and then the third range, I jump by 2 magnitudes. In this case, in the cubic interpolation version, where I'm using cubic polynomials, VSI outperforms Simpson in all 3 cases. The second graph is integral of 1 over x times a natural log of 5x. Just chose it arbitrarily. Again, we have the same kind of tables. And again, the ranges are from 1 to 2, 1 to 10, and 1 to 100. This output is for the quadratic interpolation. And again, you can see VSI, I'm underlining, it does better in the second and third range. When we switch to cubic interpolation, the VSI method outperforms Simpson's in all three ranges. Here I chose my good old root function. I figured, hey, why not? Because it goes into negative territories. I wanted to see what happens. The ranges here is from -2 to 0, -2 to 3, and -2 to 5. Interestingly here, Simpson does better than VSI in all the three cases. However, in the second and the third range, VSI is not that far behind. The error is a little bit less than a little bit more than that in absolute magnitude than that of Simpson. So it's not giving us lousy results. When I'm using cubic interpolation, where generally VSI will do better, in the third range, VSI does better, and in the second range, it's a little bit not too bad worse off than Simpson. Interestingly, I did more experimentation, and I noticed something interesting. I don't have the explanation for it, I have a guess, is when I did cases involving trigonometric function, whether the integrated function is trigonometric or whether it yields a trigonometric integrand, is that Simpson always did better. No matter how I played, I did a variety of functions, variety of ranges, and so maybe this sort of super variation, the quadratic and cubic polynomials didn't do as well as Simpson. Of course, if we apply the same in the case of the quadratic polynomial, if we use VSI with the same equal interval as Simpson, you get exactly the same results, to the T.
Do you have the comparison results with the Gaussian quadrature?
No, I didn't do that. Because here I was able to use the same number of iterations. Initially I was not, and I said to myself, this doesn't make sense. I need to put the two methods on equal footing. So anyway, that's all. Thank you.
Yes. Are you able to put an error bound on this calculation? Simpson, there's a well-known error bound for that.
No, I didn't. Interestingly, Thomas Simpson, who was behind the Simpson's method, is actually behind the Newton-Raphson root method that we know. Because Newton initially was interested in solving polynomials. And Raphson improved on it a little bit, but neither saw the generality in solving non-linear functions in general. There was Thomas Simpson who saw that this method can work for all functions, and unfortunately, he is not given any credit. So here I am giving him some credit. Yes?
The method you're using seems to sample more frequently where the slope is greater, is that right?
Yeah.
Now, that's exactly the wrong thing to do for trig functions, where you want higher sampling, where it's changing less rapidly, but it's at the peaks and the troughs. And therefore, that's where we're getting it wrong, because it's sampling frequently on the very, very smooth sides where it goes up and down on the trig function, and it's undersampling at the peaks and the troughs, which is where, in fact, you need to sample more on the trig function. So I think that explains why your method...
Yeah, because, it was like, okay, thank you, because, there was no, here, in some cases, what you can see, VSI does better. There, VSI failed all across the board. So maybe I'll go back and create a version where I reverse the sampling rate.
The ideal method for something like the 34S, which has speed but not much memory, is a cubic spline method, but that involves more programming. But it would probably work much better.
All I have to do is reverse when I'm using an increment for the maximum absolute. So just reverse those increments.
Yes.
And I'll do that. Yeah.
Tell me before the end of the day.
Okay. No, I'll do that when I go back. But it's a very simple change, and it will give us.
Again, it's not the maximal slope or the minimal slope, it's the change of slope. It's really the derivative. When the derivative is changing fast,
then that's when you need more intervals, because otherwise you're missing.
Yeah, the curvature.
Right.
Yeah, okay, yeah. Exactly.
Okay.
All right,
Thank you.
thank you very much.